Hello, class. Today we're going to talk about a little bit more in Chapter 13, States of Matter, and we're going to talk about changes of state. Yesterday we talked about liquids and solids in particular. Today we're going to talk mostly about phase changes. So here are our objectives. This is section basically 13.4 of your textbook, and the four objectives we're going to be looking at are the 6 basic phase changes. I sort of neglected talking a little bit more about plasma, so we'll talk about plasma in a little bit more detail. And then the last 2 things, we're going to be able to describe the parts of a heating and cooling curve, and then finally understand a phase diagram. Now I would ask that you pay particular attention to this last part, understanding a phase diagram, because you will have an upcoming quiz on just a phase diagram quiz. So there will be a quiz on this. This is near the end of this lecture, and this quiz is on Friday. Okay? So let's talk about the 6 basic phase changes. Now most of you, when you were in 3rd grade, 5th grade, you basically learned a lot about this, and in everyday life we do learn a lot about these things. So, but I will go through them. So for instance, when you go from a solid to a liquid, we call that melting, and heat goes into the solid as it melts. So I'm also showing you the heat movement during phase change. So again, you go from a solid to a liquid. The term for that phase change is melting, and essentially when you melt, you're adding heat into the solid. And then again, when you go from a liquid to a solid, that is known as freezing, and heat leaves the liquid as it freezes. Now this second one here, liquid to a solid, the process of freezing, and this aspect of the heat leaves the liquid as it freezes actually leads to a very interesting phenomenon. So for instance, if you go down to Florida, and let's say it's going to be a night where they explain to the farmers, the orange farmers, the farmers that grow the little oranges. So there's my orange, okay? So the farmers that grow the oranges, whatever, they grow the oranges. They're concerned that if it goes below freezing, that there will be some freezing of the fruit, and that it will ruin the fruit. So interesting, what they actually do right before the evening and before it starts to cool down is they'll actually spray water on their fruit. Okay. So they'll spray water around the fruit. And so this water's on there, and what happens is this water starts to freeze, and as the liquid goes to a solid, as this water freezes, it actually gives off, it gives off heat. And so the actual process of the water freezing actually warms the oranges. So this is a pretty interesting phenomenon where orange farmers take advantage of the fact that when something freezes, it heats. So there'll actually be a frozen layer of ice on the orange, but that is actually heats up the inside of the orange and protects it from the extreme cold once it goes below 32 degrees Fahrenheit or 0 degrees Celsius. Now in this next slide, these are the other 4 phase changes. So obviously if you go from a liquid to a gas, we call that vaporization, and that actually includes 2 processes, boiling and evaporation. Boiling is where we really aggressively add heat, and evaporation is more of a passive type of situation where the molecules slowly leave from liquid to a gas and then they go away so they don't come back and form liquid. But both processes, it's best to think of them as vaporization. Okay, and heat goes into the liquid. So again, think of them as vaporization, and that includes boiling and evaporation. But remember, heat goes into the liquid as it vaporizes, and then when we go from a gas to a liquid, that term for that is condensation, and that means heat leaves the gas as it condenses. Probably the most common way you've seen that. I know where I'm from in Minnesota, it tends to be very humid in the summer. You get out of the shower, you're pretty warm, and basically the air around you will condense and form water droplets on your skin. It makes it hard to dry off with a towel. When that happens, heat actually leaves the gas as it condenses. So gas to liquid is condensation, liquid to gas is vaporization. And then the last two instances here, I would say are a bit more rare, not as common. The first one, solid to gas. So that means you have a solid and it directly goes into a gas. That's known as sublimation. So if you've ever seen dry ice, it's just solid CO2, you can actually see the gas coming off of this. Carbon dioxide is a classic sublimator. Heat goes into the solid as it sublimates. Now the other procedure is when you go the exact opposite, which is gas to solid, and this is known as deposition. And again, when something goes from a gas to solid, heat leaves the gas as it condenses. Gas to solid, an example of deposition, probably the most common example is again in northern regions. I know where I'm from in Minnesota. Basically, deposition is how icicles form. So if you get cold enough, you can actually go directly from the gas, the water vapor in the air will go directly into a solid ice and make a pop. Well, not make a icicle sometimes, and sometimes that's called deposition. Or probably more common when it's really cold and you breathe, and if say you have a mustache or a beard, and as you breathe out, the water vapor in your breath will actually form crystals of ice on your beard and on your mustache, because it's so cold that it's bypassed the liquid phase and goes right to the solid phase. So that's known as deposition. It's kind of common for, I've seen students get these two mixed up quite a bit. So remember, solid sublimation. So starting at solid, going to gas is sublimation, and then gas to solid is deposition. Okay? So I'll give you a chance again to write down these parts over here, the movement of the heat. So again, liquid to gas, heat goes into, solid to gas, heat goes into, gas to liquid, heat leaves the gas, gas to solid, heat leaves the gas. Okay, so keep in mind, sort of as you go from the gas on down, you're usually losing heat from the system, and you're adding heat to the system when you go from a solid to a liquid to a gas, which sort of makes sense. Give you about 20 more seconds to write all this down. I know it's a lot of words. Now this is basically a pictorial form of what you just saw. So this is sort of a visual representation of what I just had in words, but it shows the 6 basic phase changes. A few things we should probably address here is, again, going from solid to a gas. You see it's sublimation and then deposition. Probably from this part here, going from a gas to liquid, they use the word evaporation. It's probably not the best word. They probably should, this word should most likely be vaporization. I'm running out of space, so I'll do it here, but vaporization, not evaporation. So again, this was evaporation. I really think the word there should be vaporization. That includes both evaporation and boiling. Condensation is the correct word. Melting is fine. They use the word solidification to go between a solid and a liquid. Solidification probably is the correct term, but of course, let's get used to just using the word freezing. I think it's a little bit more intuitive and we're used to that. So again, going from a liquid to a solid is the process of freezing. Going from a solid to a liquid is the process of melting. So again, this is just a pictorial view of what you already wrote down. If you want to sketch that out, I believe this might be in your textbook as well. But go ahead and maybe sketch that down real quick. I'll give you about 30 seconds, because on the next slide we can actually add some stuff to your sketch. So again, maybe at the top, just write gas, solid, liquid, and a little nice triangle, and then write these terms in: sublimation, deposition, condensation, vaporization, melting, and maybe here you want to use the word freezing. Okay. I'll erase this so you guys can see a little bit better. I give you about 15 more seconds to quickly jot that down. Okay, let's move on. So this next slide is basically the same thing, showing where does the heat go. It's showing it as water, an example of water. And it's just sort of showing you when heat is absorbed and when it's released. Okay. And so I think what I want you to get used to is that I like to think of ice as being the most ordered, water less ordered, and then gas the most disordered of all. And the systems, as they become more disordered, it's because you're adding heat. So if you look for the term heat absorbed here, like I like to do is follow that heat absorbed, and then heat absorbed goes up that way, and it always goes up that way. So in all these cases, heat is being absorbed, and when it's absorbed, it creates something that is more disordered. Okay, and then when you make something more ordered, more in a nice arrangement, you have to release heat, release that kinetic energy from the system. Say, for instance, from the gas, you have to release a lot of heat, has to go away. Heat has to go away, such that we have a lower system that's more ordered down here. And it makes sense because when we get rid of the heat, then it gets colder. When we add heat, it gets warmer. So we all kind of intuitively know water is warmer than ice, and so it must have absorbed some heat. Okay? So I'll give you a second to jot that down, this little graph as well. Maybe you can add it to the previous graph. I'll go ahead and just window wash all my markings here. Okay? And so, again, I like to, think of more order versus less order. I'll give you about 15 more seconds or so to finish jotting that down as well. Now, one of the things that we didn't deal with really is we talked about raising the temperature and making a gas, but what does happen if you raise the temperature to super high levels of substances? And generally, super high levels means like greater than 1,000 degrees Celsius, and between, like in this case, this is actually 1 billion degrees Celsius. You know, what goes on between 1,000 and 1 billion degrees Celsius? Okay? And the question really is, will everything just be a gas? So once you make it to a gas, you just keep heating it. People just assumed, well, you just have more and more gas moving faster and faster, and I guess the gas molecules are further apart. That's what it is. But it turns out that we learned that no, that's not what happens. At a certain point, you can affect the molecules with heat and actually strip away some of the electrons. And when you strip away these electrons, you make plasma, okay? And plasma is what we call an ionized gas, so it's still in the gaseous state, but now these gas molecules, no matter what they are, if they get heated high enough, they kind of become anions and cations on their own, okay? So the word is ionized gas, and if you look really closely at this picture here, you'll see that there's actually, you can see parts of the gas molecules are positive, these are pluses, but even these little yellow guys are negative, and I'm assuming that these are the actual electrons from the gas. These little yellow things are the actual electrons. Obviously this isn't to scale. So you get the electrons have been kind of pulled away from the gas, but you still sort of have the nucleus intact with some of the lower shell electrons, what we learned in the first semester. And so it basically, the heat is so high that it can pull away some of the electrons. And so you create this kind of weird state of matter that's really hot. It has some solid properties. It kind of flows. It has the ability to conduct electricity now, like metals. Remember when we talked about metals? We said the metal-metal bond has a sea of electrons. You can see now we sort of have a sea of electrons in here. Try to write that down, sea of electrons. That's supposed to be electrons. But yet it's a gas. It's in a higher state of matter. Okay, so plasma is, again, I said, is something not very common to us. I don't think lava is considered plasma. I'm not sure about that. Someone can maybe research that. So plasma is basically like what our sun is made out of. Now, one of the properties of plasma is that it's an extremely good conductor of electricity. This is much the same matter that I just said metals are. And it is also affected by magnetic fields. Again, most things that conduct electricity have a perpendicular effect due to magnetic fields. So that's not so surprising. And then the last thing I just want to say is plasmas do have properties, though, like gases, in that they have indefinite shape and indefinite volume. Okay? So plasmas typically will just sort of occupy space willy-nilly, and they'll have an indefinite volume. So they have properties like that are similar to gases. So keep that in mind. And again, plasmas make up, I think it's really high, it's like 99.99% of the universe is in the plasma state of matter. Okay? So I thought we should at least address a little bit of the issue of what a plasma is. So again, the best thing is, if you remember only one thing, is remember plasma is an ionized gas. Okay? Give you about 15 more seconds to finish off your notes there. And then we'll move on to some heating and cooling curves, and then finally phase diagrams. Okay. So let's talk about, kind of summarize these states of matter. And so what I like to do, though, is I have this graphic here which will kind of move us into heating and cooling curves. And so again, don't necessarily have to take these notes. This is probably just a good summary slide to go back, but you should have all these notes already. Solid, liquid, gas, plasma, and it talks about whether they're tightly packed, like here, or not packed very much here, loosely packed here, or then of course plasma, little or no order. What I really want to point out, though, is that this line here points to solids. Then notice you have to put some energy in them to make them liquids, and then you have to put more energy. This is usually in the form of heat energy to make them gases. And then finally gases, you even add more heat to make them plasmas. And so in a way you can start to see this heating, what we call a heating curve, where you go from solids to liquids to gases to plasmas, a sort of stair-step approach as you go between the two. Okay? So I just basically wanted to introduce that to you. But again, all these notes here are basically from our notes the other day. Okay? So I'll move forward. You should have all that in your notes. Again, solids are tightly packed, liquids pretty closely packed, but they slide past each other. Gases are vibrate and move freely at high speeds. And then plasmas has no definite volume or shape, and is composed of electrical charged particles. Okay? So this is sort of a summary of what we've been talking about. If you want to, you can clearly go back and look at that if you want to get more detailed notes. What I want to do is talk about a heating and cooling curve. And so go ahead and in your notes, sketch this out. What I want you to do is, go ahead and make an axis like this, just like I have here. Temperature on one axis and then heat energy on the other. Okay, so this is sort of the energy as it goes in, as you keep on adding energy, and the temperature will go up. Okay, sometimes you see these curves and they also have time. The idea is that as you go along and keep on supplying heat, the same amount of heat to the system's temperature will go up over time. So let's make this a different color. The y-axis is always temp. This axis can be increasing heat energy, but if you keep heat energy at the same level, then this can literally be time, and you'll be adding more and more heat to the system over time. So that's what I would do. And all this basically shows is that what I like about this graph is it shows the different parts. And so when you're right here, I'm going to draw a red line over it. When you're in this part, you notice I'm putting heat in the system and the temperature is going up for this first red line. And that's basically like if I have an ice cube and it's sitting there solid and I'm heating the ice cube, I'm adding heat to it. The temperature is going up, but it's still an ice cube. So believe it or not, you can have an ice cube. You can pull it out of the freezer at minus 20 degrees Celsius, and you can keep on adding heat to it, and the ice cube won't look any differently until you get to, of course, 0 degrees, which would be right here. And in that case, then, if you keep on adding heat, then there's this process by where from here to here, it actually melts. And so if you notice that in the process of melting, this is one of the most incredible things kids don't understand, and adults for that matter, during the process when say a solid is melting to a liquid, notice that there's no temperature change. Should maybe make this a different color, but notice the line is flat right there. Oops, that's not very good either. Oops, let's do this again. So again, we heat up right there. We get to this point, we start to melt, okay, because we're adding heat. And then what the point I was trying to make was that there's no temperature change. If you notice that entire time that it's melting, the temperature stays constant at this blue line. Then once all of it melts, it starts heating up again, and this is where we're in the liquid state, okay? And again, it's sort of like you have a liquid, it's at 20 degrees Celsius, assume the liquid's water. We'll assume the liquid's water. Keep on adding heat. The molecules move faster and faster, but they're still in the liquid phase. And then you get to a certain point, and then they start to, in this case, boil. One form of vaporization. They start to boil. But again, notice that when the actual boiling is occurring, there's no temperature change, and the temperature stays constant right here. Sorry, with my little blue line right here. Stays constant, okay? And likewise then, you have all this energy going into just changing the phase. So you're putting energy in. Notice from here to here, you're actually putting energy into the system. You're putting heat into the system, but you're not getting any temperature change. That's because the heat now isn't making the molecules move around faster. What it's doing is it's rearranging the molecules into a different state of matter. So finally, once you get to that different state of matter, which is a gas, you get to this point right here. And now you start heating up again, and the gas gets warmer and warmer and warmer. And then, of course, these little particles right here spread out more and more, and you're starting to heat the gas. Turns out you could keep on doing this up to a point where you'll have another phase shift between a gas and a plasma. However, this line right here, I'd have to probably draw it out about a mile or something to sort of give you an idea of where we would actually be, how high of a temperature we'd have to be to actually create a plasma. Okay? So again, this is a heating and cooling curve. And again, there's different phases, and so I'll go over them again. This part, I'll go over them in blue this time. This part right here is solid heating up, solid melting to become a liquid, now a liquid heating up, now a liquid vaporizing to become a gas, and then a gas heating up. And everything I said goes the opposite way. So if you have a gas, you cool down, it condenses, becomes a liquid. As it cools, it freezes into a solid, and then of course you could keep on cooling it. Theoretically, I suppose you could keep on cooling it until you get to a Bose-Einstein condensate. Okay? So leave that up for about 15 more seconds, but hopefully you got all that information down. Again, sometimes rather than heat energy, it just says time here. Okay, I'm going to move on. I don't want this lecture to last all day. And so again, just if you, from your previous notes, if you just didn't get all those things, if you can get these sort of 4 points, again, here's a heating and cooling curve. And what I did here was I just put some letters in, and so B is where a solid starts to melt, C is where melting is complete, D is where the liquid starts to boil, E is where it's complete, and then onwards to a gas. So if you were to fill in where is the solid, liquid, and gas, the solid would be in this part right here. Let me erase that. So if you took this part right here, that would be your solid. This part between C and D would be your liquid, and this part between E and F would be your gas. Okay? And again, E could also not only be boiling complete, E could be condensation starts, condensation ends at D, and C could be freezing begins, freezing ends at B, if you're going back the other way and cooling. Okay? Notice this heating and cooling curve has time here. Okay? So that's really all I want you to know. Turns out later on we're going to actually do calculations on this. So we're going to learn like how much energy is between D and E. We'll be able to calculate in joules, and then how much energy, for instance, is between C and D. One of the amazing things about these systems is you'll find out that sometimes it takes more heat to, for instance, it takes some solids to become liquids than it does to actually heat the liquid up. So you'll find out that this actual heat, sometimes to go between these phase changes right here, is a lot, sometimes even compared to the heat required to go between the two. So that's just something to keep in mind. So sometimes you're putting a lot of heat into a system without its temperature changing. And again, I want you to be aware, during phase change, no temperature change here. So you notice the temperature scale, we're not going higher up. So maybe write that down. Phase change. There's no change in temp. Okay? Even though you're adding heat to the system. So during a phase change, no change in the actual temperature. Okay? Let's move on. This PowerPoint's getting too long. So 2 slides to go, so I want to talk about phase diagrams. Phase diagrams are really just sort of another way to show a heating and cooling curve. They're probably a little bit more practical, though, because they're sort of give you more three-dimensional information. So this is what a phase diagram looks like. And what it is it's a plot of pressure versus temperature, and it draws some lines in, and those lines become interfaces between the solid, liquid, and gas phases. Okay? And what I'll do is I'll just sort of quickly show you what each of these sort of some of the characteristics of a phase diagram. So, again, it's a graph of the pressure-temperature relationship. It shows where each of the phases are. Okay? And these lines indicate states between 2 phases. So let's see if this works. So for instance, I have an arrow going here. This shows that all the way along that line, there's a phase change going between a solid and a liquid. So if you go from the solid to the liquid, that would be melting, and then from the liquid to the solid would be freezing. Okay? Now, the triple point, it's a temperature and pressure where all 3 phases coexist. So almost every substance has a place where all 3 phases coexist in equilibrium. So I think I have an arrow points to this, and it's the part marked A on this graph. And if you were to look at this compound, you'd see that around 0 degrees Celsius is the triple point, but that the triple point's probably quite a bit less than 1 atmosphere. Okay? So for instance, you see it's at 0 degrees here, but if you were to draw a line across from that A, you'd see it's getting towards like 0.6 atmospheres. So that means if we could somehow lower the pressure, put a vacuum on this substance, it's possible to get to a point where you can actually see the triple point where all 3 phases coexist in equilibrium. I believe when I come back I'll do a demo. I think it's with tert butyl alcohol, where you can put it under a vacuum pump and you can see it. You can see a gas, you can see it as a solid and a liquid all at the same time. But these do exist, and it's pretty cool to actually, and if you're curious, go to YouTube and look for triple points, and you might be able to see. It's kind of neat to see all 3 phases coexisting at the same time. Now the next one I want to talk about is the critical temperature. That's a temperature where a substance must always be a gas no matter what the pressure, okay? And there's really 3 things to talk about. There's a critical temperature, critical pressure, and then the critical point. And I guess I could spend a lot of time describing these, but really if I was to draw this on the thing, it's this point here, point C, up here in the upper corner. Maybe this does better. This point up here, C, and that was the critical point right there. And the critical point, if you go across to the left, you'll hit the critical pressure, and if you go down, you'll hit the critical temperature. And all that's saying is when you're at that point, no matter what, when you keep on adding, increasing the temperature, it's the temperature. At that temperature, no matter what you do to the pressure, you'll always have a gas. Okay? And the pressure is just the vapor pressure at the critical temperature. So we usually talk about a critical temperature, but there is a critical point. And the critical point is defined by these 2 here. And again, just remember where that is. It's always at this top interface between liquid and gas, and after that point, after that temperature, no matter what you do to that gas, if you're beyond that temperature, you can't make it a solid or a liquid anymore. Okay? I think there's, again, an arrow showing the critical point. So again, study this later on, but these 3 items here are basically interrelated, okay? Now, And here, last but not least, is a phase diagram of water. And let me just quickly show you some of what these are. So if you want to sketch this out, you can. So at spot number 1, if we were to look at this, two things are going on. If you're going from the gas to the solid at this point, so if you're going over this line right here, if you're going this way, that's considered deposition. If you're going this way over that line, that's the process of sublimation. So all the wet place along this line up to the triple point up here at number 3, deposition or sublimation can occur. Okay. Now, the next spot, number 2, would be ice, right? That would be ice. Spot 3 on this would be the triple point. That's where all 3 phases coexist. Okay. You can see for water, the pressure is quite low. It's around 0, but you notice the pressure has to be very low, 4.58 millimeters of mercury compared to 760, which is normal. And then 4 is where melting and freezing occur. So I think that's pretty easy to see. You go from the liquid to a solid. So anywhere, the thing to keep in mind is that anywhere along this line, melting and freezing can occur. Melting one way, freezing the other. Number 5 is obviously going to be water. Water exists there. And then 6 will be condensation and vaporization. Hope you all can see that. Anywhere along this long line between here and here is, be careful, is anywhere along that line is condensation and vaporization. Keep it in mind that right here is the critical point. Okay, and then 7 is water vapor. That's where we'll have water vapor in the air. So this is how you would interpret a phase diagram of water. You now will have a couple of worksheets. We'll ask you some things about this, about phase diagrams and how to interpret them. And you also sometimes will have to be able to read the pressure and temperature. They'll say like at what temperature, if I'm at this pressure and this temperature, am I in ice, water, or water vapor type of thing. So that's all I have. It's kind of a long lecture. I hope it wasn't too boring. And hope you have a good day. And I hope you get a better understanding of phase diagrams and states changes in phases of matter. Thank you.